Welcome to a seminar presented by the University of Alaska Fairbanks Department of Chemistry and Biochemistry. This seminar was originally given February 7, 2017. However, I am adding an audio component and publishing the seminar on YouTube for the benefit of those who may have missed the live version. I've divided the topic into two sections. First, WebMO and Mopac, and second, Basic Gaussian, which represents two levels of detail in the use of this site by students. The best way to access the WebMO website is to first visit the home page, which has a link to the login page, plus background information on the computers and programs. Go to the login page by clicking the MO graphic at the top right. Farther down the page are links to various sites, including an index to more instructional materials related to computational chemistry and molecular graphics. Your login connects you to a web server that is running the WebMO program, and that, in turn, is connected to several servers that run the actual chemistry programs, Gaussian, Mopac, and NBO Chem. WebMO provides a graphical front end for the text-based commands that run these programs. You draw a molecule with your mouse, choose some calculation options, then WebMO uses this input to construct an input file. WebMO finds an idle server, sends the job commands to it, checks the calculation progress occasionally, and sends the results back to the user in graphical form. The WebMO website can be used for both teaching and research. It's pretty easy for beginners to use, but researchers can also use it to exploit the full power of Gaussian. For example, 95% of the calculations in my 2015 paper in the Journal of Physical Chemistry were done on these computers. There are three types of user accounts on this system: guest, non-UAF, and UAF. The distinctions are made necessary by the terms of UAF's Gaussian license, which limits use to UAF faculty, staff, and students. The guest account can be used by anybody from anywhere. This account has access to NBO Chem, which is similar to Gaussian, but not quite as robust. The guest account is limited to 4 CPU hours. This is discussed in more detail on the WebMO homepage. Non-UAF users from Alaska who need to run longer jobs may do so. Just contact Professor Keller. UAF users should contact me or their instructor to obtain a WebMO user account. Currently, there are 6 compute servers available. The most recent addition is Corsair 3 that is running an overclocked 10-core CPU and has 64 gigabytes of memory. One of the factors that is confusing about computational chemistry is the many methods that are available. Here is a brief summary of this theory smorgasbord. There are 5 basic methods: molecular mechanics, semi-empirical, traditional ab initio or Hartree-Fock, density functional theory or DFT, and correlated ab initio. This is the order of increasing accuracy and increasing computational expense or time. Molecular mechanics is a non-electronic method that is very fast. It is available in Gaussian with the UFF force field and in Hyperchem. Also, a modified MM2 molecular mechanics method is built into WebMO. The quantum mechanics methods all offer approximate solutions to the Schrödinger equation, H psi equals E psi. Roughly, electrons are placed in molecular orbitals, which are described as linear combinations of atomic orbitals or basis orbitals. From the point of view of electrons in an atom or molecule, so to speak, they are trapped by a high positive charge of the nucleus or nuclei. Yet, being negatively charged, they repel each other. As a consequence, at most you can have 2 electrons per MO. And yes, the MOs tend to be in different regions in space, like px, py, and pz, atomic orbitals. However, there are additional destabilizing interactions related to the quantum properties of electrons, which together are labeled the electron correlation energy. How well the particular theory deals with this problem determines in large part how accurate and expensive it is. Okay, so we'll go through a quick set of calculations that illustrate how to run the usual gamut of computational tasks. These are: optimize the structure, check its symmetry, calculate the molecular vibrations, readjust the geometry and reoptimize if necessary, and finally show surfaces related to electron density. We'll use the dioxygen difluoride, FOOF, as an example. I made a 7-minute YouTube video showing these steps in real time. The URL is shown here, but the steps will be explained in more detail on these slides. Log in. The password is WebMO, all lowercase. Now go to the New Job menu, Create New Job. Once you've added and connected the heavy atoms, do Cleanup Comprehensive Idealized. This will add hydrogens where necessary and adjust the bond lengths and angles to nominal values. For instance, for dioxygen difluoride, oxygen is sp3 hybridized, so it gets a typical tetrahedral bond angle. Click the right arrow to continue. Computational Engine refers to the overall program, which may be capable of several different computational methods. Mopac is Mopac 2016 program, which has several semi-empirical quantum methods. Then select the server. The default is first available, where WebMO will automatically find an idle server and send the job there, or you can choose one explicitly. Click the right arrow to continue. Fill in the boxes, making sure you get the correct charge and multiplicity. Rather than clicking the continue arrow, which ends the job preparation and submits the job, this time let's check two other tabs under Configure, Advanced and Preview. Clicking Generate under the Preview button shows the actual text input file. Here you can see the Mopac commands that specify the PM6 method and other settings, and the XYZ coordinates of the atoms. This page may be edited if you have read the documentation. Click the right arrow to continue. When the job is complete, as shown on the status column, click the job name or magnifying glass icon at the right to see the results page. This page shows the energy as heat of formation and other useful information. But don't stop here. You should always check optimized structures with a vibrational frequencies calculation, especially when the molecule has torsional flexibility, twistable bonds. To test this molecule, click the New Job using this geometry and choose vibrational frequencies. When the job is done, click the job name and go to the bottom of the results page to see the list of vibrational modes. If the optimized structure is a minimum on the potential energy surface, all the frequencies will be positive. If the structure is actually a transition state or another kind of saddle point, one or more of the frequencies will be negative. This is the case here, and you should visualize the motion in imaginary vibration by clicking the Animate button icon. This is a portion of the potential energy surface of the dioxygen difluoride, where the geometry coordinate is the torsion angle. If the WebMO program builds a symmetric starting structure, as it sometimes does, this may occur at a maximum on the curve. Gaussian and Mopac geometry optimization algorithms attempt to find a zero-slope structure, but they cannot distinguish zero slope at a curve maximum from zero slope at a curve minimum. In this case, the molecule is stuck at the top of the curve, and the imaginary vibration describes the motion along the curve. It must be nudged off and re-optimized. Therefore, for a stable conformation, all frequencies must be greater than 0. If one frequency is less than 0, you have arrived at a transition state, not a stable molecule. Now, please note that the frequency calculation must be done with the same method as the geometry optimization, which is PM6. Finally, I will briefly show how to calculate and display molecular surfaces with WebMO. See the Using Mopac and WebMO YouTube video mentioned above for more details. Having run a geometry optimization, you will still need to run a separate molecular orbitals job to see the different surfaces. The MOs are calculated in every energy and geometry optimization job. However, the exact electron populations of the MOs are not available until this job is done explicitly. Open the Geometry Optimization Results page and click New Job using this geometry. Choose Molecular Orbitals. When the job is complete, go to the Molecular Orbitals table near the bottom. Each different surface, such as electron density, electrostatic potential, and various MOs, are viewed by clicking the magnifying glass icon. Calculation of the surface is actually done on the browser in your local computer, so for large molecules it may require several seconds. The properties of the surface can be changed by opening the File Preferences menu and clicking the Isosurfaces tab. The isosurface numbers are in units of electrons per cubic angstrom. The smaller the number, the farther the surface is away from the nuclei. Okay, that's the end of part 1. Now we are in part 2. I will take an overview of Gaussian software, review the relationship of atomic orbitals and molecular orbitals, explain basis sets, observe how performance is affected by the size of the molecule and the type of basis set, look at several kinds of Gaussian jobs, and finally show the standard method for modeling natural bond orbitals and transition metal complexes. The UAF WebMO site is running Gaussian 09 version D. Recently, Gaussian 16 became available, and the help web pages were updated to version 16. The Gaussian 09 web pages are easier to navigate, and since they have none of the updated material in them, these are now linked from the UAF WebMO web page. There is a new edition of Exploring Chemistry with Electronic Structure Methods, which perhaps could be called the Gaussian Bible. This book has this corresponding website that is filled with useful information, the text itself, and downloadable Gaussian input files. To review the relationship between atomic orbitals, AOs, and molecular orbitals, MOs, let's recall the MO view of bonding in the hydrogen molecule. First, consider two separate hydrogen atoms, each with one electron in a 1s atomic orbital. As the two atoms move closer, the atomic orbitals interact to form nascent MOs, one the sum, the other the difference between the AO functions. Finally, in the stable molecule, the familiar bonding and antibonding MOs are formed. They are smaller due to the electrons being attracted to two nuclei rather than just one. Here, the 1s atomic orbitals are the basis functions for the H2 MO. In semi-empirical theory, like PM6 and Mopac, the basis set consists of S function on hydrogen and S and P functions on heavy atoms. Gaussian uses larger basis sets whose orbital functions are constructed from primitive Gaussian expressions. This contains various constants and a square of the distance r inside a negative exponent. Here r is the distance between electrons and nucleus. The values of A, B, and C determine whether you're talking about an S, a P, or a D orbital. If they're all 0, This is an s orbital. If A equals 1, B equals 1, and C equals 0, this is a dxy d orbital. The Gaussian primitive by itself is not particularly accurate for describing electron distributions. However, the sum of several is more accurate. And even more important, these perform efficiently during integration mathematical operations. This is crucial because there are millions of integrations required for a normal energy calculation. Most common are the split valence basis sets, such as 631GD, also called 631G star. The 6 indicates that for a second row atom, the basis function for the core electrons contains 6 Gaussian terms. The 3 and 1 indicate that the valence basis function is split into 2 levels, an inner level described by the sum of 3 Gaussians, and the outer level described by 1 Gaussian. And finally, the D indicates that a set of 6 d orbitals are added. These are called polarization functions because they allow the basis orbitals to become distorted or polarized by the electric field that exists within the molecule. You can force Gaussian to print out the details of a given basis set. Here is the output for H2O with the 631GD basis set. The orbital function chi equals the sum of Gaussian primitives. For example, the core orbital of oxygen contains 6 terms with the exponent and coefficient of each term given in the table. The time required for a quantum calculation increases approximately exponentially with the number of basis orbitals. This graph plots the time required for a single point calculation using different basis sets. The y-axis is the log of the CPU time. The x-axis shows 4 popular basis sets going from smallest to largest. The blue data points are for the SO2 formic acid complex, which we published in JPC a number of years ago. All these jobs were done on NTEC 12 or Corsair 3 using 12 processors. Looking at one of these points, if we use the 6311++G 3DF3PD basis set, an energy job requires about 440 seconds of CPU time. The wall clock time would be about 1/12 of that, or 40 seconds. As molecules get larger, the number of basis orbitals and the time required increases. Vitamin B6, tetracycline, and alpha-cyclodextrin. On our systems, the biggest you can go practically is about 1,000 basis orbitals. If you figure a typical geometry optimization might take 25 energy calculations, 25 iterations, then you'll need to wait 2 or 3 days for your answer. This puts a severe limit on the size of the molecule that one can study with quantum methods. For small molecules, they can be studied with high accuracy model chemistry, and large molecules can be studied with less accurate models, but large molecules cannot be studied with high accuracy methods. Okay, let's go through a typical Gaussian job, say H2O using Hartree-Fock theory, HF, with the 631GD basis set in 2 processors. If you click the Preview tab and then the Generate button, this is the Gaussian input file that you see. Line 3 is where the theory, the basis set, and the type of job is entered by WebMO. Then comes the title line, the charge and multiplicity, and finally the molecular description. By default, WebMO uses the Cartesian coordinates in this section. Optimization jobs are denoted by OPT in the route section. Line 3 is called the route section. Modifying terms may be added in parentheses. For example, very tight uses a smaller gradient as the criterion for stopping an optimization. This would be, for instance, typically for optimizing hydrogen bonded complex. The WebMO input panel has an optimize and vibrational frequency item where it does one and then immediately goes and does the second. And these are often run together because of the importance of proving that a structure is an energy minimum and it has all real vibrations. Everyone has failed jobs. The most common cause is a typo introduced during modification of the input file after you click Generate on the Preview tab. Another cause is adding an extra atom during the building process. Go back and look at your structure, making sure you have the correct number of atoms. It is useful to check the .log output file. Error statements are usually found at the end of this file. For optimizations that fail to converge, the remedy may be to just restart where you left off to give the system more cycles, or re-optimize at a lower level of theory, say PM6, then restart at the desired level of theory. In the case of hydrogen bonded complexes or van der Waals complexes or transition states, try using integral equals grid equals ultrafine or superfine. This may be helpful. Lastly, if you find your structure oscillating at the end of the optimization, try doing a frequency calculation on one of the structures. It may already be an energy minimum with all real vibrational frequencies. As mentioned in part 1 of this seminar, visualizing molecular surfaces requires running a molecular orbitals job first. Looking at the Gaussian input file, you see SP, which means single point, and POP, which refers to population analysis. As we did with Mopac, to see the surfaces, you must go to the bottom of the results page to the molecular orbitals table and click the magnifying glass icon next to the surface you wish to see. For instance, electron density, electrostatic potential mapped onto the electron density surface, bonding MOs, or anti-bonding MOs are all there. Another very informative type of surface is a natural bond orbital, or NBO. These orbitals were developed by Frank Wienhold and co-workers at the University of Wisconsin-Madison. They are remixed MOs that form localized orbitals corresponding to the bonds and lone pairs in Lewis formulas. The latest version of their NBO program is version 6. Version 3, which is still serviceable for basic NBO analysis, is built into Gaussian 09. It is invoked by choosing the natural bond orbitals item under Calculation on the Configure Jobs Options page. Here is the Gaussian input file prepared by WebMO for an NBO job on methylamine at the B3LYP 631G DP level of theory. This molecule is also the subject of 2 YouTube videos related to NBOs. If you wish to also display the NBOs using GaussView program, 2 terms should be added manually to this file. The benefit of GaussView is that it will display 2 or more NBOs simultaneously, which WebMO cannot do. This is a valuable tool when illustrating donor-acceptor interactions, for example, hyperconjugation within molecules or intra- or intermolecular hydrogen bonds. The results page from an NBO job actually contains both MO and NBO data. You see the same electron density and electrostatic potential surfaces as in a normal MO job, and near the bottom of the results page are links to the NBOs. Here on the left is an sp3 type orbital carrying the nitrogen lone pair. On the right is the CH sigma star bond that is parallel to the lone pair. This orbital accepts electron density from the nitrogen lone pair. You may need to look all the way down to the bottom of the NBO list to find antibonding orbitals involved in donor-acceptor interactions. The last topic in the seminar has to do with setting up Gaussian calculations for second and third row transition metals and heavy main group elements. Due to the huge positive charge on these nuclei, the inner shell electrons are distorted by the high electron speeds. The inner shells of these atoms are best described by effective core potentials, ECPs, which are also called pseudo-potentials. Here is a typical input file for molybdenum dicarbonyl carbon monoxide complex. You have to do several things. In the route section, that is line 3, add pseudo equals read and use gen for the basis set. Both these phrases point to lines below the molecular description. The gen keyword requires that the basis set for each type of atom be described. The nonmetal atoms would get a standard basis set. The transition metal gets a special basis set, for example, lanyl 2DZ, which is substituted for the core electrons. It may seem redundant, but the heavy atom must be listed again at the bottom. These sections must be entered manually, and they must be formatted correctly. Well, that's all. The end.